Here's the key for exam 3. First question asks us to name both of these molecules. This is an ester, so that means this carbon is defined as number 1. And we number away from the OR group, and we name the R group as a substituent, so it's propyl. That is first, and then we have a space, and then we name the parent chain, which is pentanoic acid, becomes pentanoate. So because it's an ester, it becomes O8, and we have two methyls, so it's 2,2-dimethyl. We're still getting students forgetting to write dimethyl or even 2,2-dimethyl when they see two methyls here, so be sure that you're not making that mistake anymore. Pentanoate, and that's the full name for the first ester. Looking at the next compound, we have a ketone here, and it has a couple of substituents on it, 3 methyl groups. It's right in the middle of a 7-membered chain, and so it's going to be a 4-heptanone. And we'd start numbering from this side so that we have the minimum numbers for all of our substituents. We cannot start numbering from the right side. That gives us a trimethyl. It also gives us 2 stereocenters. Well, it doesn't give us that. We had 2 stereocenters to begin with. We need to recognize what their absolute configurations are. So if we look at carbon number 3, highest priority is the ketone, then the branched carbon, then the methyl. That gives us S, so 3S. And 5, again, the highest priority is the ketone, then carbon number 6, then the methyl. That gives us R, so 3S, 5R. That goes in parentheses, and that's at the beginning of the name. And then we have trimethyl, 2, 3, 5 trimethyl. Again, some students didn't condense it into trimethyl. They wrote out 2-methyl, 3-methyl, 5-methyl. That's too much. Some students didn't write tri. They just left out, they went 2, 3, 5 methyl. You got to have the tri in there as well. And then we have 4-heptanone. If you wanted to name it hept-4-one, that is also acceptable, but I prefer to put the 4 in the front. So this is the complete name for the second molecule. Okay, so now question 2 is a roadmap problem. Let's see if I can get it all on the screen here. We're basically asked to fill in boxes, either reagents or products. This first one is basically NaOH in heat. That's an aldol condensation. And we could either use this as our nucleophile and attack that carbon. That makes a 4-membered ring. Same thing if we use that as our nucleophile to attack that carbon. Both of those 4-membered rings are unlikely. So let me erase those letters. Let's use this carbon to attack that carbon. That gives us a 6-membered ring. And we know that with heat, we get the condensation, we get the unsaturation product. And you had a clue about that in this product here. There's a 6-membered ring that doesn't appear to come from this cuprate or this ethyl bromide. And so we had a clue as to what the starting material was in this box right here. Then we can add a cuprate to the beta carbon. Then we can alkylate the alpha carbon in the same step, giving us this product that I've circled in blue. Then the next stage is to add this cyclic acetal. That was not a challenge for most students, I was happy to see. Basically, catalytic acid and ethylene glycol will make that cyclic acetal. Then we are going to brominate the phenyl ring here, putting a bromine on the bottom. And we have a box to fill in. The observed changes are that we have this tertiary alcohol now from a bromine. So if we turn the bromine into a Grignard and react it with the appropriate ketone, we can get a tertiary alcohol. The next step is water and catalytic acid reacting with this compound. We don't know necessarily what goes in here or what it's going to react with, but we do recognize that we're going to lose the acetal. So water and acid will basically hydrolyze the acetal, reforming the ketone. and water and acid really aren't going to do anything to our tertiary alcohol. We might protonate the alcohol and lose water, but because we're in water, it's unlikely to do an E2 or an E1 mechanism, so it'll probably just add water right back to this tertiary alcohol. So we'll get this product here. And then it appears that we have to take this carbon and turn it into a cyanide group with an OH, and that is KCN HCN. That's how we add cyanides to carbonyls. And then lastly, it appears that that cyanide group has turned into a carboxylic acid. So this carbon is the same as this carbon. We're not adding any carbons here. We're simply changing the CN triple bond to a CO double bond with an OH. And to do that, it really just requires acid and heat. And so that's how we would solve this roadmap problem. All right, this mechanism provided a little more challenge than I expected, especially given that you were told it's an esterification reaction. Half the students who did really poorly on this question didn't even attempt to make an ester, so that was part of the issue. We have catalytic acid. We have no other reagents here. Lots of students asked, is there something missing there? No, there's nothing missing there. So what we have to do is recognize that we've got an alcohol in the starting material, we've got a carboxylic acid in the starting material. Mix those together and you get a Fischer esterification. So we can protonate. This is just a Fischer esterification. And now we have a good electrophile. We can attack that with our nucleophile, which is going to be the alcohol. We need a proton transfer. I'm just going to use HSO4 minus. It's easier to draw, but you could use starting material if you wanted to. Now we need to lose water. So I'm going to take H2SO4 again, protonate one of these alcohols. Now I have water as a leaving group. And I can push water off using a lone pair here. And I'm one step away from the product. A couple of you left this as the product. Well, that is not neutral, so that's not the product. The product is losing that extra hydrogen. And we can do that via the water we just formed. So there's our ester. One or two students actually combined a new molecule with a OH with the original molecule that we protonated here. So they made they dimerized the molecule. That was okay. I hope that you recognize this as half of the mechanism from the Peckman lab experiment. This is no different from what we did in the laboratory and on the mechanism for that. Okay, next page is the better choice questions. So let's look at these. The first one looks like we're trying to make an ester out of acetophenone, out of a ketone. We can either use MCPBA. Remember that will react with ketones and aldehydes. This is the Baeyer-Villiger reaction. And that will insert oxygens between those carbon-carbon bonds. Remember the migratory aptitude. The phenyl ring is much more likely to migrate than is the methyl. So I think if we try to do a Baeyer-Villiger here, we're going to get that product. And I think you saw that a couple times on the practice worksheet. So this would not be the product in this case. Let's look at the second one and just make sure it will make the product. Excess NaOH and Br2, that is the haliform reaction. And that would give us, and then the second step, methanol and acid, that's what we just did. That's Fischer esterification. We just did that mechanism on the previous page, so that would give us that. So definitely the bottom one will work just fine, no problems. Let's look at the next one. We have 2 pentanone reacting to form this beta keto alcohol or beta alcohol. We recognize that this bond is formed in these products, and so we're going to have to deprotonate the methyl here and attack the carbonyl. Both of these could, in theory, do this, but most students recognize this as a crossed aldol, also with equilibrium, which means we'll form a little bit of this enolate, and a lot of the starting material will be left. So this enolate could react with starting material or the aldehyde that we add. That's going to give us 4 potential products, because we could actually probably get some of this NaOH reacting with the aldehyde at this position, giving us a nucleophilic carbon right here as well. So the bottom reaction is going to give us a bunch of products. The top reaction is irreversible. Deprotonation. So that means we get 100% of the anion right there. That all can react with the aldehyde that we add, and we make the product in high yield. Let's look at the third example. We're taking this ketone to a alkene. We're adding a carbon here. So most students correctly identified that we did add 1 carbon. Whenever we change a ketone or aldehyde into an alkene, we always potentially could use a Wittig reaction. And indeed, that's one of the options here. That seems like it would work just fine. Let's explore the top one and see what the issue might be. Well, we have a negative methyl. So we could get this intermediate after protonation. Let's put the H there. And then concentrated H2SO4, that's good E1 conditions. So we could eliminate, but would we get this as our desired major product? I think most likely we would get the more substituted alkene forming for the top reaction. So I think the bottom reaction is a much better choice. The Wittig works great. It will add 1 carbon. Some students had trouble with their carbon count. They claimed that the methyl didn't appear in the product here, so that's why they didn't choose the top reaction. But the carbon I circled is the same carbon as that one. So just be aware of that. Make sure that you're accounting carbons properly and accounting for what happens to this Grignard. It does add here. It does form this C. It's just that we don't think that the alkene would form in this less substituted possibility. Page 3. First question is creation of a acid, carboxylic acid, and that's what step 1 does. Step 2 and 3 is the Hell-Volhard-Zielinski reaction, and the whole point of that reaction is simply to add a bromine to the beta position. Part B is a acid chloride reacting with an amine, and we learned in class, of course, acid chlorides have good leaving groups. They react with nucleophiles to replace the leaving group. This question was on the quiz. It is pretty straightforward. Lots of students had trouble with this amine reacting somehow with the carbonyl. LAH then will reduce the amide all the way to the amine. This question was on the quiz. Most of you didn't watch the quiz key. You're probably not watching this video either, but those of you who are, this was on the quiz. Third reaction, we're going to deprotonate at the more available carbon, more available alpha carbon, and we're going to attack the carbonyl. So that was what we're looking for here. Some of you said, well, there's no acid present, so maybe this is the product, and I accepted that. The O-, there's no acid present. So I was looking for this one, but I did accept the O-. Question D, we've got a ketone, we've got an amine, and that's followed by sodium borohydride and ethanol. We did this in lab. This is a reductive amination. First thing we do, as we saw in lab, is to form the imine. And the second thing is reduce the imine to the amine. Again, just like we saw in lab. So this is what we're looking for here. This got you 2 points. Okay, E. We have an enamine, and we're turning that into a ketone. That's simply hydrolysis of the enamine. H2O, H2SO4, catalytic. That's all we needed there. Part F. The easiest one was simply a Wittig reagent. So that would have been fine. If you wanted to show me this version of it, also fine. Some students did think, well, let's add the Grignard, and that would get us to this. And then they wanted to protonate the Grignard, or I'm sorry, protonate the alcohol product and eliminate H2SO4. And that would work. I think that would give us 50% of that alkene, right, if we eliminated this alcohol, and 50% of that alkene. So you got partial credit for this 3-step sequence, which I think will work to a point. It's not the best. The Wittig will give us 100% of the desired alkene. Moving on to this question. This is a malonic ester synthesis. And if you're paying attention, this gives you about half of the answer for one of the synthetic problems. So deprotonation followed by adding ethyl gives us this ethyl group. Then we can deprotonate the alpha carbon again, the doubly alpha carbon. We can add the alkene here. And then acid and heat will turn both of these into carboxylic acids, and one of them will decarboxylate, leaving us with a single carboxylic acid, just as though we had added these two groups to acetic acid. That is the end result of the malonic ester synthesis. It's as though we added those two R groups, or one R group, to acetic acid. So this is what we're looking for. If you showed me that, you got partial credit. Lastly, we have a nitrile reacting with a Grignard. We've seen this many times. We basically attack the nitrile. This is the intermediate. And that doesn't do anything until we protonate with mild acid and water. And what's going to happen is we're going to make the imine, but we're also still under acidic conditions. The imine will not survive those acidic conditions, so the end product is this ketone. This question was modified from the problem set. I had a lot of students that claimed that NaH was an acid, and they used the H to protonate the carbonyl. NaH is not an acid. It is going to deprotonate the alpha carbon. And I was looking for some resonance, so I just showed you one of those. We can show this. There are my resonance structures, and this anion can attack ethyl bromide. I had a lot of students claim that ethyl bromide is a nucleophile, so they decided to make a positive charge somewhere and use the bromine to attack. This is not a nucleophile. Again, like I said in class, if you're drawing some weird stuff on the exam, you need to rethink that. You know that ethyl bromide is not a nucleophile. This is a good leaving group. This is an electrophilic carbon. You know that sodium hydride is a strong base. We've seen this all the way back in chapter 7. This is H-. It is not a source of protons. It is simply a base that will remove protons from something else. So here we are with the intermediate. This was worth 4 points. Basically, we added an alkyl group to the carbonyl. Now we get to step 3, sodium hydroxide and heat. We've seen that many times already in the past 3-4 weeks. That is always basically aldol conditions. We've got two alpha hydrogens that we can remove here. So the first one gets removed. That makes a resonance stabilized anion. and that can be used to attack starting material. And I'm going to put it down here. So my new carbon is right here. It is part of a 5-membered ring. And I also have the alkoxide on that new carbon, and the ethyl is right next to it. There is probably some water present here. I'm going to use that to protonate my alkoxide. And I still have this acidic hydrogen. I'm going to remove that. I'm going to erase this red line that somehow showed up. And I get, again, a resonance stabilized anion. I can show the resonance. So that's my resonance stabilized anion. And finally, I can eliminate OH minus. That leaves me with this product, the aldol condensation product. This is the product that I was looking for full credit. So if you got here, that got you 4 points, but I wanted you to get here. And again, these conditions showed up on the problem set. Yes, it is 2 steps. It is a little more complicated, but there's no reason we should expect that NaH is an acid. That was a really common error I saw in this problem, very disappointing. And ethyl bromide, it is only ever a good electrophile. You attack the carbon with a nucleophile, lose bromide. This is not a nucleophile. Don't use this to attack or donate electrons to anything. It's not a nucleophile. Question 7. Gave you some NMR data and asked you a few questions about it. So our goal is to solve for A and B. We have a formula and we have a proton spectrum of both A and B. So the HDI for A and B, for A there's 4 carbons plus 2 minus 8 hydrogens divided by 2 equals 1. For B there are 6 carbons times 2 plus 2 minus 10 hydrogens divided by 2 is 2, I believe. So you got 4 points just for writing 1 and 2 in this paper here. Let's look at A then. We have 8 hydrogens, 3 different signals. We've got a 3 hydrogen singlet at 2.03 ppm. We know there's one degree of unsaturation, or 1 HDI. That could be a carbonyl, it could be a ring. But the fact that we have a singlet at 2.3, a 3 hydrogen singlet, probably means we've got a methyl next to a carbonyl. We've seen that many, many times this semester. So that's a pretty big clue on what we have there. And then we have a 3 hydrogen triplet at 1.15, not very far shifted. But the important, I think, point here is that we have a 2 hydrogen quartet at 4. That often means that we have a CH2. We know it's a quartet, so it's next to a methyl, and it's shifted to 4, so it's next to an O. And that about exhausts all of my formula here. So if I draw that, that is A. This is ethyl acetate. A lot of students drew this. They got half credit because the 2 hydrogen quartet would not be shifted to 4. This would be shifted to about 2. This would be shifted near to 4, but it would be a singlet, a 3 hydrogen singlet. So this one does not match the proton NMR spectrum. Now, if you look at the hint here, this problem can be easily solved without interpreting the product NMR data. We've got A. We know that A reacts with ethoxide. Second step, acid and no heat. This is a Claisen reaction. We have got an ester reacting with basically the base equivalent of its OR group. And so we will deprotonate right here. We'll use that to attack another ester, and we're basically going to end up with the OR group lost off that other ester. So this is B. Does it match the formula? C6H10O3. 1, 2, 3, 4, 5, 6. Yep. 3, 4, 5, 6, 7, 8, 9, 10, 1, 2, 3. Yes, it matches the formula. It doesn't match the NMR data. A 3-hydrogen triplet at 1.15 ppm. Well, this is a 3-hydrogen singlet, but this is a triplet, so that might work. 3-hydrogen singlet at 2, that's this one. 2-hydrogen, this should be a S, as I said in the exam room. 2-hydrogen singlet at 3.5, that's probably this 2 hydrogens right here. It's between 2 carbonyls, so it's shifted more than this signal. And lastly, 2-hydrogen quartet at 4, that is indicative of an ethoxy group. So you didn't need to interpret this data to solve for B. You just needed to recognize the reaction conditions, and once you got to A. A lot of students got A with no problem, so that was great. We had some weird answers for B. Some had 3 bonds to oxygen. A lot didn't match the formula. As I said earlier in this semester, if you don't match the formula, it's hard to give you any credit for a proposed structure here. So these are what we're looking for. The ethyl acetate ester reacts with ethoxide to do a Claisen condensation. On to the final page. So the let's look at this second one first. Looks like we have this piece here is right there. That carbon is probably this carbon. So somehow we have a double bond formed here, and we added, looks like we added two different sets of carbons. We added a 4-carbon group on one side, and we added a 1-carbon group. We've already seen adding a 1-carbon group to a ketone. We've already seen that on the exam. That's just the Wittig. So maybe we use that again here. And now the question becomes, how do I turn this carboxylic acid into this ketone? Well, there is a way to add a single or a carbon group and end up with a ketone. We could do it from the nitrile, and indeed we already saw that on this exam. Let's see, I need to draw that a little better here. So if I start with the nitrile right here, that will add 4 carbons and end up with a ketone. How do I get to the nitrile? Well, basically I need to take this carbon and turn it into a CN, or yeah, I need to turn it into a CN somehow. And I'm not sure, I think I can do that actually by turning this into the amide. SOCl2, excess NH3. That can be turned into the nitrile with, again, SOCl2 to dehydrate. We're going to remove the 2 H's, we're going to remove the O, we get to the nitrile. So that is possible. Another way would be to add this 4-carbon group to maybe a carboxylic acid derivative that might allow us to produce this ketone. So let's think about that. We can add essentially pseudo-Grignards to acid chlorides via the cuprate reagent. And that will give us the ketone. Remember that cuprates do not react with aldehydes and ketones, so they will react with this highly reactive acid chloride, but they will produce the ketone, and that will allow us to use the Wittig to add the final carbon. So this pathway here is probably my preferred pathway. It is only 3 steps, and it's pretty straightforward. Let's look at the other option on this page. This is acetoacetic ester synthesis. We're going to be able to deprotonate this doubly alpha hydrogen. We can add a couple groups. We see we've added a benzyl group here and a propyl group. And if I identify these carbons, that would be from the acetone that's left over after we do our acetoacetic ester synthesis. So the first step would be to remove the doubly alpha hydrogen. Here I'm going to add the propyl group. I'm going to remove the doubly alpha hydrogen again, and see we saw some of this on the predict the product page, where we deprotonated and alkylated in a sequence. So oftentimes on an exam, you can find some of the answers already there. So if we do all this 5 steps here, we don't get to the product immediately, but we make this thing. So that's what we get with those 5 steps. So we're still a little bit away from our product. But you can see that, let's see if I emphasize this. Those are my carbons that I drew on. Here's my propyl group. Here's my benzyl group. So now the question is, how do I make this ketone into an ether? And to do that, I think we probably need to reduce the ketone to an alcohol and then alkylate. So we can reduce the ketone NABH4 and we get that. And in fact, if I don't add any proton source to the NABH4, I'm left with the O-, and I can just use methyl iodide straight right there to alkylate that alkoxide, giving me the desired product. So this was really the only sequence, only way to do this. You could certainly flip steps 2 and 4 if you wanted to. It doesn't matter the order of alkylation there, but this is really the only way to make that first product, recognizing it as an aceto-acetic ester synthesis. All right, on to the bonus. The bonus turned out a lot better than previous bonuses. I was happy that a lot of students had no trouble with this one. So if you recognize that there's sodium ethoxide, that's a strong base, we can remove this doubly alpha hydrogen. Most students had no trouble with that. Now we have a nucleophile. That nucleophile can attack the epoxide. A lot of students try to attack the O on the epoxide. That's not the electrophilic site. You got to attack the carbon. That ring opens the epoxide. That gets me to here. You can recognize that these 2 carbons came from the epoxide. So let's do this ring. Let's do the ring closing and be done with this. We can attack the ester, pushing electrons onto the O-, making this compound, and we can lose ethoxide to bring us to the product. So this was a pretty simple 4-step sequence. As I said, a lot of students got credit on here. I was happy to see that.